In this video, we are going to discuss questions related to quiz C10S3, which is on chapter 10, section 3, which is on standing wave and the principle of superposition of wave. So let's try to look at the first question, which is question 3. Question 3 says that for a standing wave produced on a string, which is fixed at two ends, how many interior nodes? Interior nodes are nodes that exclude the two ends of the string. So it's what happened in between the two ends. Okay, how many interior nodes do you have in the standing wave with an n equals to 10? So n equals to 10 means that it's the 10th harmonic for this standing wave produced on a string. So if you are having a 10th harmonic on a string, how many interior nodes do you have? Okay, so here I've drawn 3 strings, and this string here I've placed 2 pins on both ends of the string to indicate that they are fixed on both ends. Okay, so if a string is being fixed on both ends, we know that the string cannot move at all at both ends. So we call it a fixed end. So if the string cannot move at both ends, then that means the displacement at both ends must be equal to 0 at all time, right? So what does it mean? It means that these 2 points over here are actually a node. So let's write that down. We know it must be a node. Okay, so this is fixed for a string. Okay, so now if they ask for n is equals to 10, it's a very big number, but don't worry, we can start from the first one, the fundamental, then slowly work upwards from n equals to 2, n equals to 3, then from there we can deduce what will happen if n is equals to 10. Okay, so if n is equals to 1, we know that for a string, for a standing wave, you cannot have two n side by side. In between an n and an n, in between two nodes, you must have an antinode in the middle. So you know that the fundamental wave, if you know both n are n, the simplest way of making a standing wave is to include one antinode in the middle. Right now, you cannot form a standing wave because you cannot have two ends side by side. To create a logical standing wave, you must have an antinode in the middle between the two nodes. So let's include one. So we have an antinode over here. Okay, so once you have included an antinode already, then you know that this is a logical arrangement, and a n is a logical arrangement. You don't have two a side by side, you don't have two n side by side. So this is the simplest way of creating a standing wave on a string. So we call this the fundamental, okay, or the first harmonic. So you know that this n means by the displacement must be 0. This n here means by the displacement must be 0, and at the antinode, you know that the displacement will be maximum. Okay, so you should expect the string should look like this. Okay, like this. Okay, so this is the fundamental frequency or the first harmonic. So let's look at what is the second kind of standing wave that you can produce. This right now what we have here is the fundamental, is the simplest way. So what's the next simplest way? What's the one step higher? Well, you know that at the end it's always a node, so this one is fixed. But if you want to make it slightly more complicated, you know that you must still have an A inside. But you know that if you want to make it more step higher, then you need to introduce one node inside. Okay, you want to make it slightly more complicated, so you have to introduce a node inside. So you know there's an A in between these two nodes, then it's good already. But in here you have two nodes side by side, so therefore you need to introduce a antinode in here. Then that will be the next simplest standing wave that you can produce. Again, you know that at the node, the displacement must be equal to 0. Therefore, your wave should look like this. Okay, so So you'll probably see something like one up, one down. Then it goes like this. Okay, so this is the second harmonic or the first overtone. Okay, we call this the first harmonic, second harmonic, and this one we call it the fundamental, and next one we call this one the first overtone. Okay, so when you talk about harmonic, you talk about how many times does the fundamental pattern repeat. Okay, for overtone you can think of it as it's the how many tone after the fundamental tone. Okay, so if I say it's the first overtone, then that means it's the first tone after the fundamental tone. So the first tone that is after the first tone after the fundamental tone is the second harmonic, because that's the second simplest standing wave that you can produce. And of course, if you go another level higher, then it becomes the second overtone. Okay, so let's write it down. So if it's a second overtone, then we know, let's try to draw the second overtone and see what harmonic is it. Okay, so we know both end must be N. We know this time there will be two notes inside it. Okay, because I want to make it one step more complicated, you have to introduce one more note into the string. So you know that in between two notes must have an antinote. So this will be an antinote, an antinote, and an antinote. Now you can start to draw your wave to see how it looks like. So you know at the note, the displacement must be 0. At the antinote, it must be maximum. So if you connect the dots, oops, why am I drawing such a thick line? It will be something like this. Okay. So this time you can see that the fundamental pattern, the fundamental is like this, only one curve like this. So we see that this curve repeat 3 times in here. Therefore, we know this is the repetition is 3 times. Therefore, it's the third harmonic. Okay. So you see that if it's for a stretched string, the harmonic goes 1, 2, 3, but overtone goes 0, 1, 2. Okay, we call the first as the fundamental tone, and the next one after the fundamental tone, you call it the first overtone. It's the first time you go over the fundamental tone. It's the second time you go over the fundamental tone. This one you see one time harmonic, the harmonic repeat for 2 times, then the harmonic repeat for 3 times. Okay, so that's how you call something by its harmonic and how you call something by its overtone. So we see that if we have n equals to 1, we have no interior notes. So let's write it down. If you have n equals to 1, we have no interior notes. So number of notes interior is equals to 0. When n is equals to 2, the number of interior nodes, it's 1. Okay, there's only one interior nodes over here. Next, we look at n equals to 3. The number of nodes in between the two ends of the string is 2. So the interior nodes is 2. Okay, it's a symbol I create. We never really give a symbol for interior nodes, but I will just call it by nodes, which is big N. then subscript in to mean it's interior. Okay, so you see that if it's first harmonic, you have one interior. If you have second harmonic, then you have if you are first harmonic, you have no interior notes. Second harmonic, you have one interior notes. Third harmonic, you have two interior notes. Therefore, if you are in the 10th harmonic, if you're in the 10th harmonic, I believe you know that the number of interior notes should be equals to 9. Okay, it's always one less than the number of harmonic. If it's a second harmonic, the interior note is 1. So 1 is 1 less than 2. Okay, third harmonic, the interior note is 2. 2 is also 1 less than 3. So if it's 10 harmonic, your number of interior notes should be 9. It's 1 less than 10. Therefore, the answer for how many interior notes should be 9 interior notes. Okay, so this is how you think about the question. You think about it logically, then you deduce what will happen if n is equals to 10. Okay, so let's move on to the next question. So this is question 4. Question 4 says the diagram above, which is this diagram over here, shows a standing wave in a string fixed at both ends. So again, you see that at both ends over here, you should expect them to be a node because the displacement at both ends here must always be equal to 0. You fix the end already, it cannot move. So the y must be equal to 0 at both ends. Therefore, it's a node at both ends. So they ask which of the statement is not true. First is the string vibrates the air around it. Second is the sound produced has the same wavelength as that of the standing wave. Third, the air vibrates at the same frequency as that of the standing wave. Fourth, the standing wave is a superposition of a propagating wave and its reflection. So let's analyze each statement one by one to see what is correct, what is wrong. Okay. So the first statement is the string vibrates the air around it. Well, this statement is true. Okay, how you are able to listen to a sound is like this. Let's say you see someone is playing a guitar. Okay, you are able to hear someone playing a guitar because when the person strum or pluck the guitar string, what happened is the guitar string is undergoing a standing wave. There's a standing wave produced on the string. So when a standing wave is produced at the string, you can think of it as a situation like this. So at this string over here is having a fundamental tone right now because you can see the string is vibrating this way. Okay, so these lines over here beside the guitar string, you can think of it as particles actually. You can think of it as dotted line over here like particles. So the particles, when they feel the string beside it, they will feel a push or a pull depending on how the string vibrates. So the particles around the string will get affected. Therefore, the particles around the string will get oscillated as well. So the particle beside the string is being oscillated, then you ask the particle beside it to oscillate as well. Then the particle beside it, you ask the next particle to oscillate, and the particle next to it will be oscillating. So the oscillation of the particle will travel across the medium. Therefore, you produce a traveling wave. Okay, the standing wave is at the musical instrument, but the musical instrument affect the air particles around the string to vibrate as well. Then the vibration will affect the neighboring particles to vibrate, will affect the further neighboring particles to vibrate. Then it will be a traveling wave traveling away from the guitar string towards your ear. Then when the traveling wave enter your ear, it will cause your eardrum to undergo a standing wave. The particle will hit on the eardrum, asking the eardrum to vibrate. Then the eardrum will vibrate in a standing wave pattern. Then it will transmit to our brain to generate an idea of what the sound is. Okay, so you see someone playing a guitar, it's playing at a distance. So the wave definitely need to travel. So the wave that is traveling through air to your ear, it's a progressive wave. But what is produced on the musical instrument, it's a standing wave. Okay. So the string definitely vibrates air around it. This is correct. So let's mark it down. It's correct. Next, the sound produced has the same wavelength as the standing wave. Well, this one not necessary. What you know is if the string get bent to the left, then the particle will get sucked to the left. Then when the string get bent to the right, then the particle will get pushed to the right. You know that you move the particle that is next to the string will move in the same way as the string. So if the string oscillate once, like 1, then the particle will also follow oscillate by 1. What you know is that the frequency must follow. The frequency of the particle oscillating should follow the standing wave. Okay? So therefore, you know that the air that vibrates should have the same frequency as the standing wave. But it doesn't necessarily mean that it should have the same wavelength. To see what is the wavelength, right, you have to use your V equals to F lambda. Write it down. To know this, you have to know V equals to F lambda. So for your air, right, if it's like normal atmospheric air, right, okay, the speed is usually around 340 meter per second. Okay, it's usually there. Sometimes it can be 334, sometimes 344, but it's around that region. Okay, but if you vibrate your string, this one depends on how you vibrate your string. Okay, if you vibrate your string with a higher frequency, then your F will be higher. Then you know that the wave that is produced around by the air particles will have the same frequency as the vibration of the string. Okay, then from there you know your wavelength of the wave that is traveling in the air. That's how you determine the wavelength. Okay, so it doesn't necessarily have the same wavelength as the standing wave. As you can see here, this standing wave here, it's a fundamental tone. So you know that the wavelength of this standing wave is much larger. It's actually twice the length of the string. That is the wavelength of the standing wave over here. It's about this much. That's the wavelength. But if you look at this this traveling wave that is traveling in the air, you see the distance between between two compression is much shorter. So what you can see here is that the wavelength at the standing wave over here, it's not necessarily the same. It not necessarily the same as the wavelength of the traveling wave that is produced by this standing wave over here. Okay, the wavelength doesn't has to be the same. So this statement here is wrong. Same frequency, yes, because it gets affected the same way as the vibration of the string. Okay, lastly, the standing wave is a superposition of a propagating wave and its reflection. This is true. You know that you produce a standing wave by sending one wave to the left, by sending one wave to the right, then let the wave vibrate to the left, reflect to the left, then the left and the right, they overlap together, interference. Then after that, you can explain the interference through superposition, and you see that the result of the superposition is a standing wave. So this statement here, it's true. Okay, so the statement that is not true is this one. Okay, so remember the wavelength on the standing wave produced on the string not necessarily the same as the wavelength that is in the traveling wave traveling through the air. Okay, you have to think of it as different wave. So they have the same frequency but they have different wavelength. So how do you determine the wavelength? Depends on the wave speed. Okay, so the wave speed for a medium, if it's atmospheric air, is usually 340 meter per second. Okay, so that's all for this question. Let's move on to the next question. So question 6. When you have a sound wave propagate in air, sound wave propagate in air. So it's propagating means by it's traveling. So this is a traveling sound wave, a longitudinal wave that is traveling. So you know that two particles which are 0.2 meter apart vibrate ND phase. ND phase, the meaning of ND phase is 180 degree out of phase or pi out of phase. Okay, so if The speed of sound in air is 320 meters per second. They ask for the frequency of the sound wave. So you know speed of sound is V. They ask for frequency is F. Definitely you know you relate to V equals to F lambda. So let's try to approach this question over here. So you know that V is equals to F lambda. So you know that V is 320. But you want to find a frequency. So now you need to substitute in the wavelength. So let's try to look at the wavelength. Okay, so if we have a wave over here, right here. Okay, if we have a traveling wave over here, this wave will be traveling to the right like this. So if you take 2 points that are antiphase, you can either take a crest and you can take a trough. Then you can measure the distance between them. And you can find the distance between them to be 0.2 meter. Okay, the crest and the trough are always antiphase because you can see that one is at the highest point, one is at the lowest point. So if you just focus on the particle over here, this particle is at this phase over here, whereas this particle is at this phase over here. So we know that this whole complete wave cycle here has a phase difference of 2 pi. So you know that in between here and here, the phase difference is pi. Okay, so pi, the phase difference is pi. That means it's 180 degree out of phase. 180 degree out of phase means by its antiphase. Okay, there are many points that are antiphase as well. You can take this point and this point. These 2 points also have a phase difference of pi as well. So these 2 points are antiphase. So if you measure the distance between these 2 points, I believe you get 0.2 meter as well. Okay, so these 2 points are 0.2 meters. So you know that for the wavelength, which is from here to here, wavelength is from here to here, the wavelength should be 0.4 meter because it's 2 times of 0.2 meter. So therefore, now you know your wavelength is 0.4 meter. Okay, so now once you know that, you can start to determine your frequency. You know V is equals to F lambda. Your V is 320. Your frequency is what you're interested to find. Your wavelength is 0.4. So from there, you can know your frequency to be 800 hertz. Frequency is equals to 800 hertz. So the answer is this one over here. Okay, so that's how you solve the problem. What you need to be careful is you might be thinking antiphase. Antiphase, standing wave, sound wave. You might be confused whether it's standing wave or a traveling wave, but you see it propagates in air. Therefore, you have to think of it as a traveling wave. So if you look at a traveling wave, you have to forget about standing wave for now. Okay, because if you look at the standing wave, right, for a standing wave, any particles in between two nodes, so this is node, 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 all the particles that is in between two nodes are all vibrating in phase. So everything here are in phase. Okay, then everything on the other next pair of nodes, everything in here are in phase as well. Everything here are in phase. But between this phase and this phase, it is 180 degree out of phase. Okay, so what am I trying to say here is if it's for a standing wave, you pick any particles on the left hand side of a node. If you compare with any particles that is on the right hand side of the node, you see that they are always 180 degree out of phase. Okay, So this side of between these two nodes, everything is now at its peak. Between these two nodes here, everything is now at the trough. So you know that everyone here is in phase. They are all reaching the peak at the same time. Everyone here is R in phase as well, but everyone is reaching the bottom at the same time. So if you compare anything on the left hand side of this node, if you compare with anything that is on the right hand side between these two nodes, you see that any particles here are 180 out of phase with any particles over here. So when you look at 0.2 meter apart, you might be confused between what particle and what particle, because any particle here and any particle here are out of phase. So you might be confused. But the main mistake that happens to you is you think of it as a standing wave, but that's not the case. The question here is asking about a traveling wave. So if you focus on traveling wave, you know that the distance between 2 points that are out of phase is always fixed. Okay, there is only one particle and one particle that are out of phase in the wave cycle. So if you know the distance between them, you can determine the wavelength, and from there you can determine the frequency. Okay, so that's how you solve question 6 over here. So let's move on to the next question. So if you look at this question here, question 7 says that the diagram above shows a metal wire stretched between two supports P and T. So the diagram is over here. So we have a metal wire, which is this wire over here. Then it's stretched in between point P and T over here. So this is P, this is T. Okay. So P and T are 4x apart. So if you look over here, there is 4x in between point P and point T. Okay. 3 small pieces of paper are placed at position Q, R, and S. So you are going to place a piece of paper here, a piece of paper here, and a piece of paper here. A total of 3 pieces of paper being placed in between point P and point T. So when the wire is vibrated at certain frequency, the small pieces of paper at R remains on the wire, but small pieces of paper at Q and S drop off. So you know that R here, because the paper remains, you know that at that point the wire is not vibrating. So the wire is not vibrating at that point, that's why the paper remains on the wire. If the paper drops off from the wire, then we know there's a lot of vibration happening there, therefore the paper falls off. So you should expect point R here to be a node, whereas point Q and S to be an antinode. Okay, so now they ask you to find what is the wavelength of the wave which is produced at the wire. Okay, so let's try to solve this question here. Again, we mentioned just now, Q and S will be an antinode, R will be a node. If we fix it at point P and point T, so these 2 points here must be a node as well, because we have already stretched the wire between two support P and T. It's like you're pressing P and T, you're not allowing it to vibrate, so P and T will be a node. So let's write it down. P is a node, T is a node. You know R, the paper remains, so it's a node. So A antinode is at Q and S. So once you have determined that already, you can draw your graph. You know that if this is your equilibrium line, then displacement is 0 at the node, whereas at the antinode it can be maximum. Okay, so once you have determined that, then you can draw your graph. Okay, usually I see people when they usually draw one solid line, then they draw another one which is dotted line. Okay, I think that makes sense. Okay, so this is the standing wave that is being produced on the metal wire right now, and now they ask you to find the wavelength of the wave that is produced. Well, if you see here, this is just one wavelength, right? So if this is just one wavelength, then we know that the wavelength will be 4 times of x. That's why the answer is 4x. Okay, quite straightforward. Or else if you are seeing a situation where the wave is something like, let's say, up, down, up, something like this, then you know that this is 3 over 2 of lambda. Okay, there's 1.5 lambda over here. So you have 1 lambda over here plus half lambda. So if this is the case, just imagine you have another case like this. If this is the case, then you need to know that 1.5 lambda is equivalent to 4x. Then lambda will be equals to 4 divided by 1.5x. Then you know 1.5 is 3 over 2. Therefore, it will be 4 times 2 equals to 8 over 3x. Okay, so this is how you are going to solve this kind of question. Okay, but for now, you know that right here you have 1 lambda. So for here, 1 lambda is equivalent to 4x. So straight away you got the answer. But if it's another case, then you have to solve it like this slowly. Okay, so we know straight away the answer, the wavelength for this situation here, it's 4x. Okay, so let's move on to the next question. Question 9. So question 9, you have a student attach one end of a hose to a lamppost. At the other end, he stretch it out and perform a quick up and down motion to produce wave on the line. So if you were to imagine a situation, you can draw a lamppost. Lamppost, it's a street light lamppost. Okay, so this is the ground. You have lamppost. So you have a student over here. So this student is stretching the hose. Hose is your water rubber pipe. Okay, so you are stretching a hose which is tied on one end to the lamppost. Then after that, this student's hand perform a quick up and down motion. Therefore, a wave will be produced. Okay, so of course this wave will be traveling towards the lamppost, and from there the reflection will also occur, and these two incident and reflected wave, they will overlap, and through the overlap we produce a standing wave. Okay, so that's the situation right now. And now they ask, how can you increase the wavelength? Okay, so how can you increase the wavelength means by how do you make the wave more loose, something like this. How do you go from like this to like this? Okay, so V is equals to F lambda. You want to increase the lambda. There are two ways if you want to increase the lambda. So first is if you keep V constant, then how do you change the lambda? It's by decreasing the frequency. Okay, so how should I write it? So if V, let's say V is equals to 10, then frequency is equals to 5, lambda is equals to 2. Now if you want to increase lambda to 5, then you have to bring down your frequency to 2. So the process here, you see that the frequency decrease. So frequency decrease, what does it mean? You shake more, you shake faster or shake slower? Well, we shake slower, right? So if you shake slower, then 1 second probably produce one wave cycle. If you shake faster, then probably 1 second you produce many wave cycle. So if you shake slower, you bring down the frequency. So you need to know, so you know that half of the answer is you shake it for fewer times per second. So now you can eliminate these two answers already. Okay, the next way of increasing the wavelength is if you keep the frequency constant. Okay, if you keep the frequency constant, that's what that means by right, the next situation, v equals f lambda. Let's say initially it's 10, it's 5, it's 2. Now you want to increase this to 5, then you also keeping frequency constant. That means your speed will have to increase. So your v will have to increase. So your wave speed will increase. So how do you increase wave speed on a medium? Okay, if it's a rope, for this situation, the wave is traveling on the rope. So for a wave that is traveling on the rope, you know that the wave speed on the rope is determined by this equation here. Okay, the square of the tension divided by the mass per unit length. This is how you can determine the wave speed that is traveling on the rope. Okay, it's the wave speed of the wave traveling in the rope, and this wave here will incident and reflect to produce your standing wave. Okay, but this wave speed here is the speed of the wave that is moving to the right, and it's also the speed of the wave that is reflected moving to the left. Okay, and these two waves will overlap to form the standing wave. Okay, so this v over here, you know that you want to increase it. So you know there's two ways of changing the v. First is by increasing the tension, or by decreasing the mass per unit length. Okay, so for this case, if you want to change the mass per unit length, you have to change it to a lighter rope. But you are not changing a rope, you are still keeping the same rope. So what you can do is change the tension only. Okay, mass per unit length we are not changing, because if you want to decrease the mass per unit length, that means you have to change to a lighter hose, probably a hose which is thinner, or a hose which is smaller. Then you can decrease the mass per unit length. Then you can increase the wave speed. This is one way of doing it, but we are not changing the hose. So what can we do is to increase the tension exerted on the rope. That means we pull the rope tighter. If we pull the rope tighter, then we will increase the wave speed. So if we increase the wave speed, then it will cause the wavelength to increase if we keep the frequency constant. Okay, when you think about what increase cause what to increase, right? You have to keep one of the variable constant, then it's easier to analyze. Okay, but of course, if you increase the speed and decrease the frequency both at the same time, then of course the wavelength will increase much faster. If you do both, then of course the wavelength will increase a lot. Okay, so you know that you have to increase the tension. Tension need to increase. Therefore, your answer should be increase the tension. Therefore, this is the answer. This is not the answer. Or your answer is this one. Okay, stretch the hose tighter and shake fewer times. Then you will see that the wavelength will be much larger. Okay, so this is how you solve this question over here. Next, question 11. So below it's a picture, well, this is the picture of a standing wave on a 30-meter long string. So this string here has a length of 30 meter and it produces a standing wave on this string over here. And as you can see here, this is a fundamental tone. Okay, first harmonic. So what is the wavelength of this standing wave? Well, you know that this is the length of the string. The length of the string is 30 cm, 30 meters, sorry. Okay, and you know for this standing wave over here, there's two notes, and in between the two notes you have an anti-node. Okay, you learn from the lecture notes or from videos that the distance between two notes, two successive notes, is always lambda over 2. So lambda over 2 is equals to L for this case. Therefore, lambda is equals to 2L. Therefore, 2 times of 30 meter is 60 meter. Therefore, you know that the wavelength of this standing wave is 60 meter. Okay, another way of doing it is, you know that this wave looks like this. Okay, so you know it's fixed at these 2 points. What can you do is you can extend the line to see the total with distance to cover a wavelength. You extend the line. This is not the actual string, but if you extend the line, then you can know this is one wavelength. And if you get the distance over here for one wavelength, and that is the wavelength of the standing wave. Okay, so you know that you repeat the fundamental pattern twice, then you get one full wavelength, right? That's why you can have 30 meter over here, and you need to extend it one more time. Therefore, you know the wavelength is 60 meter. Okay, so that's another way of determining the wavelength of the standing wave. Okay, so let's say if you have another standing wave pattern, let's say your standing wave pattern looks like this. Okay, so if your standing wave pattern looks like this, then this is the length of the string, right? Then you know over here there's 1 lambda plus 0.5 lambda. So you can do 1.5 lambda equals to the length of the string, and you can determine your lambda by taking L divided by 1.5. Or if you know this length of the string here is 30 meter, then you can try to determine what is the length for the wavelength over here. The wavelength will cover from here to here, right? So this is the wavelength. You know it's 2 over 3 of L. So that's one way to do it straight away as well. One is by looking at it from a more graphical approach. Look at how do you get one wavelength from the standing wave over here. A more graphical approach, or you rely more on mathematics. You know that the distance between two nodes, where are the nodes over here? You know the distance between two nodes, it's lambda over 2. Okay, so you know that there are 3 distance between the node. Okay, so there are 3 lambda over 2. It's equals to L. So you know that it's 3 over 2 lambda equals to L. That's also another way of doing it. There's many ways to determine the wavelength just by knowing the length of the string. The important thing is you need to know the concept, you need to have a strong concept, then you know you can look at it from either a graphical approach or to determine it using a mathematical approach by knowing that the distance between two nodes is always lambda over 2. Okay, so that's how you solve question 11. Let's move on to the next question. Okay, so you have a string fixed at both ends. So I draw a string here which is fixed at both ends, and this instrument will play an A note. An A note is like a piano A, right? Okay, so A is 440 hertz when plucked. So if you have a string here and you pluck it, the frequency of the sound produced is 440 hertz. For this particular string over here, if you pluck it, when plucked, you produce a 440 hertz. Now, what you do is you press the string hard to the fret at 1/3 of the way along the string. Okay, so if you don't play any kind of string instrument, it might be difficult to understand this statement. But fret, right, it's the board that is behind the string. If you play guitar, you need to press on the string in order to play different notes, right? When you are pressed, right, you are pressing against a backboard, right? There's a board behind the string, so it presses the string onto the board. So that board is called the fret. Okay, so there's many lines, of course, so you see what length of string you want, then you press on it. Okay, so when you press the string hard to the fret at 1/3 of the way along the string, that means that this is your string. You are pressing it at 1/3 away from one end. So you are splitting the string into 2 sections. One section is 1/3 of the total length. One section is 2/3 of the total length. You are pressing on this point over here. Okay, and if you read back the statement, Now you plug the longer side. That's why if you see my diagram here, I am drawing a standing wave on the longer side. When I press here already, right, that means the wave won't appear here anymore. If I plug on the right hand side, then there will be a standing wave produced on the right hand side. If I plug on the left hand side, then there will be a standing wave produced on the left hand side. But now I'm plugging on the longer side of the string over here. Okay, so now they ask you likely hear a sound with frequency of how much. That's what the question asking for. Okay, so how do you approach this question here? It's we need to determine the lambda, and we not necessarily need to determine lambda. Let's work through it together. Okay, so you know that here there's two nodes here, so you know that the distance between two nodes must be lambda over 2. Distance between two successive nodes must be lambda over 2. So you know that this distance here is lambda over 2, so you know that lambda over 2 is equals to L. Okay, lambda you know it's equals to V is equals to F lambda, therefore lambda is also equals to V divided by F. So you can substitute V divided by 2F equals to lambda. Okay, now this is the wave speed on the string. Okay, remember you are doing the wave speed of the string over here. Because this lambda here is a lambda on the string over here, this frequency is the frequency of the string being oscillating. So all these are about the string. So of course the speed here will be the speed on the string. Okay, so if it's the wave speed on the string, you know it's related to V equals to square root of T divided by mu, the tension divided by the mass per unit length square root. So for this situation here, you are not tightening the string, you are not losing out the string. You are using the same tightness of the string. Therefore, you know that the tension is not changing. Next, you are also using the same string, you are not changing to a lighter string, you are not changing to a thinner string. Therefore, you are not changing your mass per unit length as well. So you are keeping your tension constant, you are keeping your mass per unit length constant. Therefore, your V will not change for both situations. For both situations, the V are the same. Okay? So if your V is constant, so you can shift it to be like this. V is equals to 2F then the length. Okay? So this is the first situation. Let's move on to the second situation. For the second situation, you know that there's two nodes over here. So know that the distance between here will be lambda over 2. Okay, so for here, lambda over 2 will be equals to 2L divided by 3. Okay, the distance between two nodes that are next to each other, right? One node to the next node, the distance must be lambda over 2. Okay, this is fixed. So lambda over 2, you know, it's equals to 2L over 3. And of course, you know that this will be a new lambda. This lambda will be different from the lambda in the first situation. And also the length here is still the same length of the string. The total length of the string is still L, just that now the new length of the string is 2L over 3. But the L is still representing the whole string over here. So this L for the second situation is the same as the L in the first situation. They are representing the total length of the string. Okay, what for the standing wave right now, you are definitely using this portion of the string only. Therefore, the length that we put is 2L over 3. But what this L represents is still the total length of the string. Therefore, the L in the first situation and the second situation are using the same L. We are not don't need to put a prime in front of it, prime on top of it. Sorry. Okay. Next, we also need to use the equation V is equals to F lambda. You know that this lambda will be a new lambda because that's what they are asking for, the new frequency. But the lambda, it will be a new frequency, it will be a new lambda. Okay, it will be a new lambda. So you can also put prime on top of this. So this is a new frequency, new wavelength, then the wave speed, you call it like this. Okay, so now if you change this equation, then this equation will be v prime divided by 2f prime equals to 2l over 3. You know that for the first situation and the second situation, the wave speed will be the same because you are not changing the type, how tight you stretch the string. You are not changing the mass per unit length of the string. So you know the v over here will be the same as the v prime over here. So you want to compare it. So let's bring everything else to the right hand side, leaving v prime on the left hand side. So v prime will be equals to 4 f prime l divided by 3. Okay, so once we have done that already, we will need to compare between v and v prime. So for this situation, it's 2 frequency length times 4 new frequency length divided by 3. We know that both sides has this L, we can cancel it out. Then if we rearrange our equation, we can see that this is 6f divided by 4, which is equals to 3f divided by 2. So this is 3 over 2. The previous frequency here is 440. That's why it's 3 over 2 divided times 440. So the answer will be this answer over here. Okay, you see here, I'm not applying any advanced maths. I'm just using what we see in the diagram as the foundation of our understanding. I'm starting by saying that by seeing what I can see on the diagram. I see that the distance between two successive nodes must be lambda over 2. Then lambda over 2, we know it's equals to the length of the string. Then after that, from the lambda, I need to change it to wave speed and frequency, because I know that wave speed will be constant for both situations, so I can compare the wave speed later. So that's why I need to change it from lambda to become v divided by f. Then I put v on one side, leaving everything on the other side. So do it for the first equation, and do it for the first situation, do it for the second situation. Then I compare the wave speed because I know that they have the same tension, same mass per unit length. So once I compare it, I can see what's the relationship between the new frequency and the old frequency. Okay, so that's how you can solve the problem over here. And as you can see here, if I shorten the string, I will cause my frequency to be higher. This is a higher frequency. That's why when you play guitar, right, when you shorten your string, when you press nearer to where you pluck, when you press nearer and nearer, you pluck a higher and higher frequency sound. Okay, that's why the string will dong, 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 dong. Okay, you will get higher frequency if you pull your hand nearer to the place where you pluck. You are shortening the string, therefore you are increasing the frequency. Okay, so that's how you solve question 12. Next question. So question 13 says that if you are given this equation here, then it says if this string is making a sound, the V in the above formula should be substitute with the speed of the sound in the air, or with the speed of the sound in the air, or speed of the sound traveling on the string, or neither, or either of them. You can substitute in this or this. So what should you substitute here for the V over here? Whether it's the sound in the air, speed of sound in the air, or the speed of sound in or the speed of the traveling wave in the string, or either of them you can substitute. Okay, so to understand this concept more properly, let's talk about the difference between standing wave and traveling wave. Okay, so usually when we talk about sound, right, there's always some kind of instrument that is producing the sound. The instrument can be our throat, our voice box, or it can be a speaker, or it can be a guitar string, it can be a flute, or it can be a kazoo, or anything. Any kind of instrument that can produce sound, they are actually producing sound by actually through standing wave actually. So if you have a guitar string, when you pluck, what happens on the guitar string? It's a standing wave. If you have your mouth, when you're talking, right, you're vibrating the air inside your voice box or whatever, like trachea, I'm not sure which part, okay, but you're vibrating the air particles inside your this portion, and the vibration, it's a standing wave kind of vibration in your throat. Okay, if it's a speaker, as you can see here on the speaker, you can see the speaker is vibrating this way. You don't see the wave traveling to the left, you don't see the wave traveling to the right. So this is a kind of standing wave. Okay, but how does this standing wave here translate into sound that you hear? Well, actually, when this kind of standing wave is happening, you know that there are air particles around the speaker, right? So when there's air particles around the speaker, when the vibration, when the standing wave happens, what happens is the particles around or particles neighboring the speaker membrane or the string are being pushed and pulled by the speaker membrane or the string. So if your string bend this way, then you're pushing the particles to the right. Then when your string bends the other way, then you get sucked back to the left. So the vibration of the air particles around the string follows the standing wave of the string itself. Okay, so this particle, there must be another particle beside it. So when this particle push to the right, then of course the neighbor particles will get pushed to the right as well. That's why the wave field propagates through these air particles that are around the standing wave over here. So when they push, they will push all the neighboring particles, push, 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 therefore the wave propagates. When the membrane bend to the left, then it will pull, 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 pull. So all the particles will get pull, 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 pull to the left. So this is how from a standing wave we can produce a traveling wave. So the traveling wave, if it's traveling through air, then you can see the air particles are vibrating in this kind of fashion. Okay, but you need to differentiate where is the standing wave, where is the traveling wave. The standing wave is at the musical instrument that is producing the sound wave. Okay, so the sound wave is actually a traveling wave that is coming out from the musical instrument, and this is the wave that actually enters our ear, and our ears, inside there's eardrum, so the traveling wave hits on our eardrum, causing our eardrum to create a standing wave. Actually, our eardrum will get vibrates left, right, left, right, left, right at this, then you send signal to our through auditory nerve, I think, to our brain, then it will translate to the sound that we hear. Okay, so the process of how the wave gets from your guitar to your ear is through traveling wave. But what is producing the traveling wave is actually a standing wave of the musical instrument. Okay, so you need to know this thing very clearly. So of course, there's standing wave here, there's progressive wave here. So that means by you have let's use red color. Here you definitely you have your own wave speed, you have your own frequency, and you have your own lambda. So this is your standing wave speed, this is your standing wave frequency, and this is your standing wave wavelength. Of course, for the traveling wave that is moving out, you have your V, your wave speed, you have your frequency, you have your wavelength. So this one is for progressive wave, progressive wave, progressive wave. So for standing wave and progressive wave, how do we compare between their speed? How do we compare between their frequency? And how do we compare between their wavelength? Okay, one thing we can know for sure that is the standing wave for the frequency of the standing wave must be equal to the frequency of the progressive wave. Because as I say, if you get bent to the right, then the particle get moved to the right. So when you bend to the left, then the particle will get sucked to the left. So it's vibrating in phase. The vibration on the speaker membrane or on the guitar string, it's in sync with the neighboring particles. So if the guitar string oscillate once, then the particle will also oscillate once. So the frequency of the standing wave and the frequency of the progressive wave should be the same. Okay, next, if you look at the wave speed, right, you know that for the standing wave, if it's a string, you know that it depends on this equation over here. Okay, so if you substitute in the tension exerted on the string, you substitute in the mass per unit length of the string, you substitute in these two things, then what comes out is the wave speed. So what is the wave speed on the guitar string, right? Doesn't depend on how you plug the string. Depends on what kind of frequency is happening on the string. The only two factors that are affecting the wave speed on the string is how tight is the string and how heavy is the string. These are the two only things that affect the wave speed on the string. So if you fix the tension, if you fix the wave mass per unit length, even though you plug it at a higher frequency or a lower frequency, your velocity will not change. Okay, your velocity is fixed because you are not changing a tension, you are not changing a mass per unit length. So even though you are changing the frequency, the wave speed will not change. What will be changing? Well, it's the lambda that's changing. So if you increase your frequency, what will happen is your wave speed will remain constant if your tension is constant, if your mass per unit length is constant, then your wave speed is constant. So if you are not changing how tight is your guitar string, and if you're not changing your guitar string, then the wave speed on the standing wave will be constant. So if you increase the frequency, you bring down the wavelength. And of course, if you bring down the frequency, you increase the wavelength. So by changing the frequency, you are changing the wavelength. You are not changing the wave speed of the wave produced on the guitar string. Okay, so this is standing wave. For progressive wave, if it's on air, if it's in air, then you know that it's around 343 meter per second. This one it's usually around this range. Okay, technically there's an equation. The equation is V equals to bulk modulus divided by the density of the air. Okay, this one is called bulk modulus. It's out of syllabus. Bulk modulus is related to what you learned in the next chapter, Young modulus. Okay, then this one is density. Okay, so technically what changed the wave speed of the wave traveling in the air? It's the bulk modulus and the density of the air. Okay, that's why if you change the air from normal air to helium, you are changing the tone of your sound, right? Why will you change your tone of your sound? Because you are fixing the lambda, you are fixing your lambda, but if you increase the wavelength, then you increase the if you increase the wave speed, you increase the frequency. Let's write it down. Okay, I'm getting confused myself already. If you change it to helium, you are bringing down the density. The helium gas is less dense, so if you bring down your density, then you will increase your wave speed. If you increase your wave speed, if you keep your lambda constant, then your frequency will go higher. That's why your sound will sound squeaky if you change it to helium gas. Okay, it's because you change the wave speed. But if you are using atmospheric air, which is most of the case, if you're not changing to any different kind of air, then you should expect that the speed is always 343 meter per second. So this is for the progressive wave. So I'm going to erase all the things that are not in your syllabus, so don't worry too much about it. So these are not in your syllabus. Okay, so for the progressive wave, you know that the speed is always 343 or 340, depending on what the question gives. You know that the frequency of the progressive wave always follow the frequency of the standing wave of the musical instrument. Okay, so now you know your frequency, you know your wave speed, then you can determine the wavelength of the wave that is traveling in air. So this wavelength here will be different from the wavelength over here. Okay, because this wave here it's not 343. This wave for the standing wave here is determined by this equation. It's not 343. So if it's not 343, even though you have the same frequency, you will get different lambda for the standing wave and the progressive wave. So you need to be clear where is the standing wave, where is the progressive wave. Okay, so now you know that already. You know that this equation here is for the standing wave. Therefore, this V here will definitely be the speed of the wave on the string. Okay, you might be seeing, traveling wave, but I'm writing standing wave over here. Why does it make sense? Well, the stationary wave never travel. So technically there is no speed for stationary wave. Stationary wave remain at its position, right? It's not progressing to the left, not progressing up to the right. But you know that when I'm saying the speed over here is representing the speed of the wave that is traveling to the left and the speed of the wave that is traveling to the right. You know that these two waves will interfere, then the result of the interference is the standing wave. Okay, so when I say the speed of the standing wave, I'm not saying the speed of the standing wave. I'm saying the speed of the progressive wave that produce the standing wave. Okay, so yeah, my explanation might be a bit confusing here. So it's the traveling wave speed, but I know that this traveling wave here will interfere with the opposite direction traveling wave to produce the standing wave that you observe over here. Okay, so this is the difference between standing wave and progressive wave. So you find the standing wave at the musical instrument, you find the progressive wave at the air particles around the musical instrument. Okay, so the answer should be the speed of the traveling wave on the string, because this is the equation for standing wave. So this is the speed of the traveling wave that produces the standing wave. Okay, so that's all for this question. Let's move on to the next question. One of the resonant frequency of a pipe closed at one end and open at another end is 300 Hertz. So you know that one of the frequency that can cause a resonance in the pipe is 300 Hertz. Okay, so you might be a bit not familiar with the idea of resonant frequency, so I'll explain that as well. Okay, so which of the following are possible resonant frequencies of the pipe? Okay, so you know that if it's closed at one end and open at another end, then this will be the air column that is closed at one end. If you want to draw it as a diagram, you know that this diagram here will look open at one end, closed at one end, something like this. Okay, so these are the formula for the frequency. If you want to express it in terms of wave speed, you can use this formula. If you want to express it in terms of the fundamental frequency, you can use this formula. For now, we are going to use this formula over here. Fn equals to n f1. So this is the fundamental frequency, whereas this will be the frequency at the nth harmonic. Okay, so they say one of the resonant frequency is 300. So if 300 is one of the frequency, then they ask which of the following are possible resonant frequency. So we know that n over here can only sub in 13579. So we have to look at all these value here to see whether we can construct fn and f1. Then the n inside here must be either 13579. Okay, so what are the frequency given is 100, 200, 400, and 500. So let's write it down. 100, 200, 400, and 500. Okay, so now we will try to construct the equation for Fn equals to n F1 to see whether it's able to produce an equation where the n is either 1, 3, 5, 7, 9, 11, and so on. Okay, so 100 is definitely smaller than 300, so we know that 100 is more suitable to be the fundamental frequency. Fundamental frequency is always the lowest frequency. Then if you multiply it by the n over here, you get a larger frequency. Okay, so we'll sub in 100 for F1 for the fundamental frequency. So you sub in 100 for the fundamental frequency, you sub in 300 for the resonant frequency given over here. So what will be the answer for n? Your n will be equals to 3. So 3 is one of the value here, so this is fine. Okay, next you look at 200 hertz. 200 hertz is smaller than 300, so 200 is definitely more suitable to be the fundamental frequency. So you write down 200 over here, then you know 300 is over here. So if you do your maths, you know that the n over here is 3 over 2. 3 over 2 is not one of the option here. Therefore, you know that this is definitely not a logical wave to use. So you see there's 200 here, 200 here, and 200 here. That's why you know all these answers here are wrong. And the answer is actually this one. Okay, but let's continue to look at the others. So you have 400, you have 300, 400 and 300. 400 is larger, so it'll be on the left hand side. 300 is more suitable to be the fundamental frequency. So 300 you put over here, n you put here, 400 you put here, then you know that n is equals to 4 over 3. Again, our value is 13579, so this is not logical. So if you see this 400 here, then it's wrong, double wrong. Okay, next you look at the next one, 500 and 300. 500 is larger, so it should be on the left hand side. 300 is more suitable for fundamental frequency. So 300 and 500. Okay, so now if you do your question here, you might be seeing that it's 5 over 3, so isn't it wrong as well? So is this one wrong as well? Not really. Okay, how you can think about it is, if you change your fundamental frequency to be 100, then if you put in 500, then your n will be equals to 5. So n equals to 5 is a valid one. So that means if you have 500 hertz, then you know that the fundamental frequency should be 100 hertz. The fundamental frequency is 100 hertz. Get what I'm trying to say? The fundamental frequency is 100 hertz. Then the third harmonic is 300 hertz, which is the value being given over here. And the fifth harmonic is 500 hertz, which is the value given over here. So now if you bring down your fundamental frequency to 100, then you know that 300 and 500 can be resonant frequency for this pipe over here. So therefore, this value actually makes sense. Okay? So, yeah, that's why the answer is 100 hertz and 500 hertz. Okay, so if you try it for 400 hertz, right? Let's say 400 hertz, you might be thinking, oh, can I do the same thing like this? I set 100 hertz as my fundamental frequency. If I say yes, my fundamental frequency, then 400 here, you get an n of equals to 4. But if you see here, there is no 4, there is no even number. So this is wrong as well. So this is not the correct one, this is not correct one, this is the correct one, this is the correct one. Therefore, the answer is 100 hertz and 500 hertz. Okay, so I say I want to explain about resonant frequency. So the idea is like this. On a pipe, right, you can set the particles in the pipe to vibrate at different frequency. It can be vibrating at 1 hertz, 2 hertz, 3 hertz, 4 hertz, slowly increase until 1000 hertz, 2000 hertz, and so on. Okay, so what you can do is, let's say you have a kind of device that can set the particles vibrate at a certain frequency. Let's say a speaker. Okay, you can use electricity to vibrate the speaker at certain frequency. Then this is what you observe. Okay, so let's say you have a dial, like a knob, like your fan, you can turn 1 2 3 4 5, right? Let's say you have a knob that can go from 0 to 500 hertz. Okay, so let's say now it's pointing at 0. So when it's pointing at 0, you hear nothing. Okay, now you slowly turn up the dial. So let's say you turn it up to let's say you turn it up to 50, then you turn it up to 100, then you turn it up to 200, turn it up to 300, turn it up to 400, turn it up to 500. So resonant frequency is like this. So we know that from this situation here, our fundamental frequency is 100, then our resonant frequencies that make sense is 500. Okay, so if you are able to change the frequency of the speaker vibrating, right, you see that for this pipe over here, let's say you install a speaker here to vibrate the air in the pipe, then you see that at 100 hertz you hear a loud sound. Okay, but this loud sound is at the lower pitch. So lower pitch is like then if you change it to 110, 120, you hear the sound goes away. So it will go like let's say I change the dial, from here it will like they will disappear. The sound disappear because it's no longer in resonance. Then you slowly increase the frequency again, you increase, then when you're near 300, it will then the sound will disappear if you go over 300. Then you continue to increase, but 400 is not 1, right? So you hear nothing as well. Hear nothing. But when you're near 500, you hear. Then you go greater than 500, then you disappear again. Okay, so resonance only happens at a certain frequency. In this case, it's happening at 100 hertz, 300 hertz, and 500 hertz. So you hear louder sound when you are at resonance, and when you are not in resonance, the standing wave produced in the pipe is a very random kind of wave, so you cannot hear a loud sound from it. Only at this certain resonant frequency can you hear a loud sound with the correct pitch. So you see the pitch here get greater and greater. That's why before this is then is then is you hear the pitch go up. Okay, so this is the idea of resonance. Okay, it's a poor demonstration, but I hope you get the idea. Okay, so next question. So question 16. A stationary wave is formed inside a tube which is open at both ends. So you see that both ends here are not closed. So which diagram show the location of the node and antinode in a tube for the first overtone? Okay, first overtone means by it's the next tone after the fundamental tone. Okay, so let's try to think about it. So when we look at a situation where they ask for a first overtone or second overtone, it's always the best to start from the fundamental tone. Okay, so how do we determine what does the standing wave looks like for a fundamental tone? Look at this pipe over here. The pipe over here is open at both ends. So if you think about it, if your particle is being placed at here, then this particle here is not being locked in its position. If there is a wall here, then your particle is here, then your particle near the wall cannot vibrate, right? Because there's a wall blocking it. But if it's a pipe that is open, then this particle here has room for you to move. So if it has room for you to move, then it will vibrate, it will oscillate. So if the particle is at here, then there's no obstruction, there's no nothing to block it from oscillating. You should expect this particle to be an antinode. Okay, so this particle here will be an antinode because there's nothing blocking it from moving. If you're looking at the string, right, the string is usually fixed at both ends, right? If you fix the string already at both ends, then the two ends of the string cannot vibrate, right? So in that case, it will be a node. But in this case, if it's a pipe, then your particle is at the end of the pipe. There's plenty of space for it to move, right? So you should expect it to move. So if it's moving, then it should be an antinode. So you know that both ends here should be an antinode, but you know that an antinode and an antinode cannot be side by side. In order for it to be logical, you need to introduce a node in the middle. Okay, so this will be the most simplest wave that you can produce in an open pipe for now. Okay, so if we try to draw the standing wave pattern inside, then we can draw it like this. We know that antinode will be maximum, node will be not moving. You think of this as the equilibrium, huh? So then antinode will be maximum. So your graph should be something like this. Or the other one, you can draw a dotted version like this. Okay, definitely not the best drawing. Okay, so this will be the fundamental tone for a pipe that is open at both ends. Okay, so if you want to make it the first overtone, we know that this is the fundamental tone. So the next tone after the fundamental tone is of course the first overtone. So the first overtone, you know there must be antinode on the both end, but you know you want to make it slightly more complicated. So you want to make it slightly more complicated, you have to introduce one more node inside. Okay, so before that you have one node only, but now you have two nodes. But when you have two nodes and they are side by side, you know it's not logical. Therefore, you need to introduce an antinode in the middle. So now if you draw a graph over here, then you know that at these 2 points, you should hit back to the equilibrium position. And at the antinode, it should be maximum. So now if you sketch the graph, you know that the graph looks like this. Okay, and on the other side, it will be like this. Okay, so this will be the first overtone. Okay, so if you know this is the first overtone, you can straight away check for the answer, right? Then the answer will be this one. Okay, so this is how you do it. Okay, so what I want to discuss right now is this how the particle move? Like if you have a particle and the particle is vibrating, let's say at here, does it mean it's vibrating up down like this? No, okay, this one, it's, you can think of it like this. Okay, you can think of this graph here as the graph of y against x. Okay, so y means the displacement from the equilibrium position, x means position. Okay, but you know, right, if you are in the pipe, right, if you vibrate the particles in the pipe, if this is your pipe, right, your particles, if you blow on the particles should be vibrating like this, right? If you blow on the pipe, the particles won't vibrate like this, right? You whoo, and it should be vibrating back and forth. So the wave that is produced, that is traveling in the pipe, are actually longitudinal wave. It is not a transverse wave that is happening in the pipe. When you blow into the pipe, you are creating a longitudinal wave that is traveling back and forth in the pipe. Okay, so what does this graph tells you here is, if you see a positive, okay, I'll pick a few points. I'll pick 1, 2, 3, 4, 5, 6, 7. So what does it tell you here? It's a positive displacement to the right. So you should expect your particle here to be more to the right, somewhere here. Okay, your particle has moved to the right by a little bit. Okay, for your particle over here, you should expect the particle to move also to the right, but less than just now. So somewhere around here. So for the particle around here, you should expect it to also move slightly to the right, something like this. So over here, you should expect 0 movement. So at here. So over here, you should expect a particle to move in the negative direction, which is to the left by a little bit. This one, you're expecting a particle to move also to the left by a bit more. This one, you're expecting a particle to move to the left but much more. So you can see that all the particles are now compressing towards the node. So this is what's happening here. Okay, your node here is it's the center in which all the particles will compress towards for this situation. Okay, now if you look at the first overtone, you look at the first overtone, let's pick few points, 1 2 3 4 5 6 7 8 9. So now if you look at this, that means you are traveling slightly to the right. This one, you're traveling slightly less to the right. This one, you are not traveling at all. This one, you are traveling slightly to the left. This one, you are traveling a lot to the left. This one, you are traveling slightly to the left. This one, you are not traveling. This one is traveling slightly to the right. This one is traveling much more to the right. Okay, so you see that there is a region here. This region here, what's happening here? It's a compression. And you can see what's happening here. They are all moving away from this dot over here. So what happened here? It's a rarefaction. R-A-R-E, rarefaction. Okay, before this, all you can see is just one compression like this. Okay, of course, compression at later time will become rarefaction. Okay, rarefaction happens if you change to look at this dotted line over here. Okay, and if you change to look at this dotted line over here, then you will observe that this will become a rarefaction. This will become a compression. So that's the idea of what you are drawing actually in the pipe. Okay, you are seeing where is the compression, where is the rarefaction happening inside the pipe. Okay, so that's what I want to explain regarding stationary wave produced in a open pipe. Okay, so let's move on to the next question. So you have a stationary wave of various frequency and it can be produced in a tube open at both ends, X and Z. Okay, so X and Z here are open, so it's an open pipe and you can produce stationary wave of various frequency. Now the midpoint of the pipe of the tube is called Y. So both ends are called X and Z, the midpoint we call it Y. Now they say which of the statement of the stationary wave is correct. Now they ask where must be a node, where must be an antinode. Okay, so let's try to analyze it. So if it's an open pipe, we know that the particles over here, they have many space to move around, so you should expect an antinode over here. Okay, so what happens in the middle is if it must be a node if it's a fundamental tone. If you go up by one step, then you have to make it slightly more tricky, introduce one more node, then it'd be like this. Then you go up one more step, then you introduce 3 nodes inside. Then you know that all these nodes must be separated by an antinode in between. That is what happens if you go up from n equals to 1 to n equals to 2 to n equals to 3. Okay, so let's look at each of the statement here. There is always a node at x. So x is the left hand side of the pipe. Left hand side of the pipe, is it a node? No, it's an antinode. So this is wrong. Next, there's always an antinode at y. Y is the center. You can see that at the first harmonic, it's not an antinode, it's a node actually. So if it's a node, right, then this statement here it's wrong. Okay, the antinode only happens when you are at n equals to 2. Okay, so it's not necessary, it's not a must for it to be an antinode at y. It alternates between node, antinode, and node at the center of the pipe. Next, there is always a node at Y. So Y is the center. Is it always a node? No. It alternates between node and antinode at different harmonics. Next, there is always an antinode at Z. So Z is the right hand end of the pipe. You can see that it's always an antinode. That's why this statement here is correct. So the answer is this one. Okay, so just now I just call it n equals to 1, I just call it n equals to 2, I just call it n equals to 3. How do I know that? It's actually, I need to, it's not that simple, it's straight away n equals to 1, n equals to 3, and n equals to 2, n equals to 3. How should I do it is, I should draw the graph first. I know this will be the graph, and I know this one, the graph will be like this. This one, the graph will be like terrible. Let me draw it again. Don't rush. Start by labeling the dot first. Okay, then when you start to draw. Okay, so this is the standing wave pattern for an open pipe. How do I know it's n equals to 1, n equals to 2, n equals to 3? Remember the n here is representing harmonics. So when we say harmonics, we say how many times the fundamental wave pattern repeats. So we see here the fundamental pattern looks something like this. So over here we see this thing happens 2 times. So 1, 2. That's why n is equals to 2. Here you can see it happens 1, 2, 3. That's why n is equals to 3 over here. See, I split it here, I split it here, then it become 1, 2, 3. That's why this is the third harmonic. If I look over here, this is 1, 2. That's why this is the second harmonic. Okay, for an open pipe, the n goes from n equals to 1, n equals to 2, n equals to 3. But if you move to a closed pipe, right, which is one end is closed, one end is open, right, then you notice that if you construct this thing, you see that it will go from n equals to 1 to n equals to 3 to n equals to 5. There is no n equals to 2, there is no n equals to 4 if it's a closed pipe. Okay, so that's why we say for a closed pipe, there's only odd harmonics, there is no even harmonics. So there is no second harmonics, there is no fourth harmonics for any closed pipe. Okay, so we need to be aware about that as well. Okay, so this is question 17. Let's move on to the next question. So next question say, what's the main function of the finger holes in the flute? Okay, so a flute looks something like this. You should have a mouthpiece, mouth opening over here for you to blow on it. Then it's a pipe that is open at both ends. So there are various holes over here which we will call as finger holes. Okay, so what is the function of the finger hole? Well, it's like this. Okay, let me open the hole here. Okay, so this is where you blow into. Okay, so when you blow here, right, what happens if you open all the holes here is you form a standing wave that looks something like this. You form a fundamental. Usually for a musical instrument, the most prominent sound that you hear is the fundamental tone. Okay, so this is what happens if you open all the finger holes. Okay, but let's say today if you close the finger hole, if you close the first finger hole, what will happen is you produce a standing wave that looks like this. Okay, because now it's open here. So you form both ends. The one end is here, the another end will be here. Okay, that is what happened if you close the first finger hole. And let's bring it slightly further. So what if you close all the hole? Let me change another color. So let's say what if you close all the hole here, then your open end will be open here and open here, right? So your wave that you form is something like this. Okay, so when you are changing the finger hole, right, when you are pressing on different holes, right, what you're doing is you're actually lengthening or shortening the pipe. Okay, you are setting where you want the pipe to open. So if you set where you want the pipe to open to be somewhere further away from the mouth blowing area, then it'll be a longer pipe. If you open up all the holes, then you are bringing the open area, open region to be a region that is closer to where you blow. Then it become a shorter pipe. Okay, so when you press on the finger holes, what are you doing is you're actually shortening or lengthening the pipe actually. You're changing where the open end is. If the open end is further away, then if the open end is further away, then you produce a wave with greater wavelength, or for a greater wavelength and a lower frequency. Okay, if you open up all the hole, then it will be a shorter wavelength or a higher frequency. Okay, you can try this out. If you close all the hole and you blow on the flute, it should be a lower tone. Be a, but if you open up all the hole and you blow again, it'll be a higher tone. Something like that. Okay, you can go try it out yourself. Okay, so this is question 18. So let's move on to the next question. Question 19. The air in open pipe is vibrating with a second harmonic. Okay, so this is open pipe, open at both ends, then it's vibrating with second harmonic. And a small speck of dust is located at half of the way down the pipe. So you place a dust at the center of the pipe. Now you ask, what does the pipe do? So again, let's try to draw. This is second harmonic, right? So you need to draw n equals to 2. Okay, so let's draw n equals to 1 first. You know that at both ends, it should be an antinode because there's plenty of space for the particle to move. So in the middle, there should be a node. So the fundamental one should look something like this. Okay, so you know second harmonic. So you know that the fundamental pattern should need to do it 2 times. So you should see 2 times the fundamental pattern in your pipe. Okay, so this is n equals to 2. This is n equals to 1. So now you place a particle at the center over here. So if you place a particle at the center over here, you should see that the displacement over here is the greatest. That's why this is an antinode actually. Then if you try to complete the diagram, you should see that this is the AN, AN, A. Okay, so if you place a particle at the center, you should expect antinode. So antinode, you should expect greatest amount of vibration. Okay, so the vibration is in which direction, whether it wiggles up and down or wiggles back and forth. Well, I mentioned in the previous question that if you're blowing in a pipe, you should expect all the particles to be like this, right? It should be back and forth, right? When you blow, it doesn't go up, right? When you blow, it should go like this. So it's a back and forth, it's a longitudinal wave that is traveling back and forth in the pipe actually. So you should expect the particle to wiggles back and forth along the length of the tube. So this is the length of the tube. This is the length of the tube. The particle is vibrating along the length of the tube. Okay, so this will be the answer. So that's it for this question. Let's move on to the last question of this quiz here. So a clarinet is basically sealed at one end. You blow into a very narrow hole, but the flute is open at both ends. Okay, so later we'll see a picture of how people play a clarinet and how people play a flute. So if you have a clarinet and a flute of equal length, how would the fundamental sound like? Okay, so let's look at the diagram. So on the left over here, you have a person playing clarinet. On the right hand side, you have a person playing a flute. Okay, if you can see here, this person here, when he's playing a clarinet, the whole mouth is closing up one end of the tube. So this thing here, it's your mouth. Your mouth is closing up one end of the tube, and at the other end of the tube, it's open. Okay, we call that the bell of the clarinet. Okay, so this is a pipe that is closed at one end, open at one end. So it's a closed pipe. Okay, if it's one end closed, one end open, we call it a closed pipe. It's not two end closed only, we call it a closed pipe. If both ends are closed, right, you cannot make a sound. You cannot make the wave vibrate at all. So there is no two end closed pipe. If we call it a closed pipe, that means it's one end open, one end closed. Okay, so for a flute, you can see the person is blowing on top of the flute. So when you're blowing a flute, right, you can go watch video. When you're blowing on the flute, right, you don't put your mouth cover the hole at all. You're just blowing onto the hole. So the hole is still open. That's why you call it an open end over here. You are just blowing at the open end. Okay, you are not closing your mouth at the open end. At the clarinet, you're closing the open end. You're using your mouth to close it up. But for flute, you're blowing at the hole. You're not closing up the hole. So that's why this one is left open. Of course, the other end is open as well. Okay, so we say this clarinet and the flute has equal length. So I draw these two pipes here to be having equal length. So now what does the fundamental sounds like? Let's try to investigate it. So we know for this clarinet here, because it's a closed pipe, you should expect here to be a note because the particles over here not able to move, not able to vibrate freely. So it's a fixed end, so there should be a note over here. Over here is an open end, so you should expect an antinote. So the fundamental should looks like this. Okay, so this is the fundamental for a clarinet. For a flute, you know that both ends are antinote. So in the center, there must be a note. So if you put the center over here, then it will be like this. Okay, sorry, my drawing is getting poorer and poorer. So this is how the flute looks like. How the standing wave in the flute looks like for fundamental tone. Okay, so you can definitely see that this one has a greater wavelength. This one has a shorter wavelength. Okay, how do you determine it? Well, in this diagram here, there is no n and the next n, so you cannot do lambda over 2. But you know that the distance between the note and an antinote here, the distance should be lambda over 4. Okay, because if there is a next note over here, then the distance should be lambda over 2. So therefore, you know that the distance between the note and the antinote must be lambda over 4. Okay, so this is the situation. So the length of the pipe, here, it's L. Therefore, lambda over 4. Okay, let's do it here. For clarinet, lambda over 4 is equals to L when you are in fundamental. So therefore, lambda is equals to 4L. For a flute, you know, between A and A, the distance should be lambda over 2. So lambda over 2 is equals to L for the fundamental of a flute. Therefore, you know that for flute, lambda is equals to 2L. So this one is definitely a longer wavelength. This one is definitely a shorter wavelength. Okay, that's what you know for now. The next thing, you have to come back to V equals to F lambda, because now you know about the wavelength, you are interested to know the frequency, because you are saying that how does it sounds like. Sounds like you have to talk about either loudness or the pitch. Okay, if it's loudness, then greater amplitude means greater loudness. Okay, as you turn up the volume, that means you are increasing the amplitude of the sound. Pitch is frequency. If you increase the frequency, the pitch go higher. So it goes from to that one is changing a pitch. Okay, so now you see the question here, they say it sounds lower or sounds, yeah, sounds lower or higher. That one is definitely pitch. So we're interested with pitch, so we're interested with frequency. So we are interested in frequency, that's why we use this equation. Because we know for lambda, for the wavelength, clarinet, we have a longer wavelength than flute. Okay, clarinet has a greater wavelength than flute. This is what you know for now. And you know that for frequency is always 343 meter per second because it's the same air. You're not changing it to any kind of air, not helium, not, yeah, it's just normal atmospheric air. So therefore you know that this one is constant for V. So if you have a greater wavelength for clarinet, that means you have a shorter, and you have a lower frequency for your clarinet. So frequency for clarinet should be lower. Your frequency for flute should be greater. Okay. You need to do the substitution yourself. If this one, if the lambda is greater, then the frequency have to go down because your V is constant. When lambda is greater, you need to bring down the frequency because your V is constant. Therefore, if your lambda is greater, if your wavelength is greater, your frequency should be lower. Frequency should be lower, that means the clarinet will sound lower. Therefore, the answer is the clarinet will sound lower. Okay, if you are in a school band or if you are in a marching band or somehow, something like that, then you can try to compare the clarinet if you do the fundamental tone, and for the flute when you do the fundamental tone, that's like, yeah, if you do a fundamental tone, you hear that the flute sounds higher in pitch. Okay, whereas the clarinet sounds lower in pitch. Okay, so that's the idea for how a closed pipe is different from a open pipe. Okay, so this is question 20 and it's the last question for our quizzes chapter 10 section 3. So I hope you benefit from a video. We have discussed about 14 questions here. So if you have any question, feel free to contact me about it. Thank you very much.